Yes, hello friends. So this is the video tutorial for today's GFG problem of the day, traveling salesman problem. This is a hard problem, but I think if you know the exact topic on how to solve, if you have solved problems like this becomes a very easy problem. So let's straight to the problem first. Given a 2D matrix cost of size n, where cost ij denotes the cost of moving from city I to city j, your task is to compute a tour from city 0 to all of the cities such that you visit each city exactly once, and then at the end come back to city 0 at minimum cost, right? So I will, and the constraint is that n is at max 10 days, n is 15 at max. Okay, so what is a traveling salesman route basically? See, the graph given to us, okay, one second. The graph given to us is fully connected. Why? Because see, the adjacency matrix or the cost matrix here given to us gives us the cost of going from I to J. But it never says that there is not a route between I to J. It just gives you a cost. So there would be an edge from each I to each J, or each starting vertex to each ending vertex, and it will have some cost. Right? So this is a fully connected graph, something like this. Now what it says is, let's start from zero. So here it is a one index graph. Let me make this a zero index graph. This would be zero, this would be one, this would be two, and this would be three. Right. So we start from zero. Then we can go to one, we can go to three, we can go to two. Right. So let's start from zero and let's go to one here. So that would give me a 10 cost. So I'm here now. Right. I'm here now. From one, I cannot go. I cannot go back to zero because see, I have to start at zero and I have to end at zero. That is the only time I can visit unindexed. Right? At the starting and the at the ending. Now from one I can go to three, I can go to two. Like let's go to three here. So then we are at this indexed and that would give me a cost of 25. Now from three, I cannot go back to one because see, each vertex has to be visited only once. I cannot go back to one. I have to go back to I can go only to two. Right. So at two, 30. Now I'm at this index and at this vertex, and from this vertex I have to go back to zero because each other vertex has been visited. Now I go back to zero, that would cost me 15. Now this is one just traveling salesman path. Again, there could be many traveling salesman path. From we started from zero and went to one, right? We can also start from zero and go to three, right? So this yeah, this would give me some cost. Another traveling salesman path would give me some cost, and we want the minimum cost for all of them. Okay. This is a very famous problem, TSP, traveling salesman path, very famous problem. There are two solutions to this. One is greedy, and other is DP solution. Now, greedy solution is not optimal, obviously, and this like for good test cases, this will fail. This will fail. But I have seen some problems where you have to solve traveling salesman problem, and n is like 1000. So in this case, you have to use greedy solution, even though it is not optimal and won't give the right answer. Okay. So why this greedy is not optimal and will give me the wrong answer? It's so what is greedy solution here? Like let me take this matrix, right? Let me take this matrix. So what would be our greedy solution here? We are starting at zero. Okay. We are starting at 0. Now from 0, what is the minimum edge to a non-visited vertex? So the minimum edge from a non-visited vertex is this one, right? This one, because 0 is visited, so this 0 we won't consider. We will consider this one, and this would give me a cost of 1000. Right? 1000. Now we are at 1, we have visited 0, we have visited 1. So now we'll again consider the minimum edge from 1 to a non-visited edge, vertex, that is 2. So we'll go to 2. This will again give me 1000. Now we are at 2. We have visited 0, we have visited 1, we have visited 2, we have visited everything, but we have to go back to the starting vertex. That is vertex 0. So that would again give me 1000. 1000. Right, 1000. So that will give me a cost of 3000, and this is the correct answer for this test case. But this test case I can slightly change and convert it into this graph. Right, so again, let's start from 0. Right, we are starting from 0. We'll go to 1. Now from 1, see, what is the minimum cost from 1 to any other unvisited? So we have visited 0, we have visited 1. Now the unvisited here is 100. So this is misleading us basically. Because it's saying let's pick 100 here. So our answer would be 1 plus 100 plus, then from 2 we'll go back to 0. That would give me 1. So that would give me 102. But if we were a bit optimal and we actually, rather than going from 0 to 1, which was giving us the minimum, we can go to 2 here. So if we went directly to 2, that would give me a cost of 5 here. So let me make it here. So we go from 0 to 2, so that would give me 5. Then from 5, I can go to 1 using this 5 plus 5. And then from 1, we can go back to 0. This would give me 5. This is 105. This is 15. And we have seen how the greedy solution can mislead us and give us the wrong answer. So if we cannot use DP solution, how can we solve this? It is an actually a bit mask DP question. What is a bit mask? See, if we were considering a DP solution here, what would our states be? Our states be that the current vertex we are currently on, right, from U, and the visited array, right? Basically, we are doing a DFS traversal, and if we forget about bit mask and DP, let's just do a backtracking solution. So, what would be a backtracking solution? Basically, be that you are at vertex U, right? From vertex U, you have to consider all of them, all of these uh, all of you have to go to all these vertex V, which are not visited, are not visited, right? And if this is not visited, we'll go to it, we'll add cost uv to our solution, get one answer by going to one v, then we'll go to another v. Let's say this is v1, this is v2, then we'll go to v2, get this get the answer of going from u to v2, and store the minimum of them, right? This would be our backtracking solution. How the problem of backtracking solution would obviously be, because this would become exponential. If this becomes exponential, and this becomes exponential on the number of edges. Number of edges is 15 into 15, right? So this becomes 2 raised to power 225, I think so, and this would obviously TL. So we cannot do this. But see, if what are our states, or what is the changing parameters? That is, one is that vertex you are currently on, and the other is visited array. Now this visited array is a 15 size array, right? It basically is true, false, something like this, right? True, false. That this 0, 1, 2, 3, 4. So this basically means 1 and 3 are not visited. So if let's say we are at vertex 2 here, so from 2 we can consider an edge from 0, 2 to 3, and from 2 to 1, right? That is fine. But we cannot, how now, if we were to use DP on this, we can DP on U, that is fine. DP of U. How will you DP on this visited array? This is an array, right? You cannot store an array as an index. How this you cannot do directly, but you can optimize this using a mask. So what is a mask or a bit mask? The idea here is, see, here this is a 15 cross 15 size vector, right? And each of the values either 0 or 1. So rather than using an array, or basically it's a boolean of what would be a visited boolean visited 15, right? I'm saying that actually storing this in our DP thing is hard. So rather than doing this, I can convert this into an integer. How is basically create a 15-bit integer, and if this bit is set, so let's say the integer is currently, so here this basically array would get converted to, see, this is true, so we'll have one here. Okay, one second. Yeah. Okay, yeah. So this is true, so 1. This is false, so 0. This is true, so 1. This is false, so 0. This is true, so 1. So this basically, rather than storing this visited, now we'll just store this integer. What is this? 1 plus 2 plus 4, 8, 16. So this becomes 16 plus 4 plus 1. That is 21. Right, so do you understand how we convert this visited into the integer? So basically, if the idea is that this integer, let's say the integer is 1101. So if 1101, this basically means that the 0, 1, 2, 3. If the 0th bit is set, that means you have visited the 0. First bit is not set, so this is a not visited. So 2th bit is set, so we'll have visited. 3th bit is set, we'll have visited. Does this make sense? I will show you in code how do you convert this, like, visited into this mask, and how do you change this mask. But do you understand this? How we can now store this? Now, what's the advantage here? So we saw that our visited thing will now become a mask, and this becomes a mask of size 15 or 2 raised to power 15. So this becomes as 2 raised to power 15. This is of 15. So now can I dp this into 15 into 2 raised to power 15? My number of states becomes this. Now this is very less. This is very less, and we can create a dp on this, and then our solution would have a time complexity of, see, a number of states of 15 into 2 raised to power 15. And from each state u, we can have 15 different states, right? So basically u, from u the maximum number of non-visited would be 15, right? The total 15 edges. So that becomes 15 square into 2 raised to power 15, and this would not really, this is very less. So this would work. This is allowed. Let me show you the code here. So if you don't know what like mask is and how do you do a DP mask solution, this would be a bit tricky of an implementation. But I will try to like show you how we can do this, and then you can try it on your own and read through like what are DP, what is DP mask, and all of those things, right? So yeah, let me show you my code here. So it's a pretty simple code actually. But yeah, if this is the first time you are seeing mask and this, obviously this would be confusing. Okay. So basically create two global variables. N is basically the number of vertices in our graph. So n is cost dot size here. All set. So what is all set here? See, when would we say, what would be a base case here? So base case here is, let's say if n is 4, that is first, 2, 3, 4, that is the this thing. Then 0th visited, first is also visited, second is also visited, third is also visited. We have 4 vertices, we have visited them all. What would the mask of this be? Mask of this would be like 8 plus 4 plus 2 plus 1, 15. So how do you calculate this mask, or how you can do this is just see 1 into n minus 1, or that is here 1 raised to the power 4, that is 16, minus 1, 15. That is basically see. This is a 1. This is 1 right shifted by 4, or 2 raised to the power 4. We just subtract 1 from it. We'll have this. So this is basically a all set, and this all set we'll use when we are at the this is our base case. So if mask is all set, that we have visited all the vertex, now we have to go back to the starting vertex. So that would give me a cost of cost I comma 0. As I said, we'll use a DP solution here. So if this is basically memorization, that if this DP and I comma mask is visited with this, we have already seen this, we have already calculated it, we'll just return this memoized solution. If not, we'll calculate the solution. How we calculate the solution is, see, we are at I vertex, or are at I vertex. We'll check, should we go to the jth vertex? How we can check, we should we go to the jth vertex? We'll basically in the mask check if this if the jth bit is set or not. See, if we are at 1101, 1101, and we are at second vertex, right? So the state is 2 comma 1101. This is in binary, right? So should we go from 2 to 0? We'll check if 0th bit is set. It is set, so we should not go. It is already visited. For 1, it is not visited. Let's change the mask to this 0101. So if for 1 it is not visited, we can go to it. For second, again this is visited, we should not go to it. For the third, this is not visited, so we'll go to it. So this is what we are doing. Okay, one second. Yeah. So if this bit is not set, so mask and this jth bit is not set, we'll go to it. We'll create a new mask. In new mask, I will add this rep. So let's say again. So 0101. Let's say I am visiting this vertex. So what would be a new mask? It would be this mask, and I will add one bit here. So I'm just doing a bitwise OR here, right? This will change to 0110 or 0111. So these are all visited, and we are also visiting this. So a new mask becomes this. So this becomes a new mask. As I said, we'll do backtracking. So answer equals to minimum of cost. We are going from I to j plus recursive of j comma new mask. And finally, we'll in our DP we'll store the final answer and return it. Yeah, we'll create how we'll call this function is recur from 0. We are starting 1 because see, we are at vertex 1. So what is the bit mask of 1? Bit mask of 1 is just this, like in all of them are 0 1, and see, only the 0th bit is set. That means that we have already visited the 0th vertex, and which we have done because we are starting from 0, right? So we'll call this as recur 0 comma 1 comma cost, and yeah, we can submit this. This works. I will leave a link to the code and all of those things. You can try to, like, you should try to code this out. This would make a sense to you. You guys, if you code this out on your own, you will debug it, all of those things. Yeah. Thanks for watching. Bye bye. How do I code this?